Hi, everyone. Thank you for joining us for another webinar in our series here at Jasco. Today, we're going to be talking about understanding, optimizing, and analyzing thermal melts with Dr. Sherry Hemmingsen. Dr. Hemmingsen brings extensive experience in analytical chemistry and molecular spectroscopy, with 14 years in the academic arena and the last 20 years in the analytical instrument industry. She received her doctorate in analytical chemistry at Duke University, working with Linda McGowan on novel steady-state and lifetime characterization of humic materials, where she cultivated her love of spectroscopy, chemometrics, and expertise in fluorescence. Following her passion for instrumentation and education, she enjoyed both teaching and research in analytical environmental chemistry at a small liberal arts university before making the transition to the scientific instrument business. She has served in diverse technical roles, from product management and applications to field sales, and is thrilled that all of these have provided limitless opportunities to actively engage her love of teaching and spectroscopy. Sherry, please start. And just a comment, if you guys can please hold any questions you have till the end of the webinar, that would be great. So thank you.
Great. Well, thank you, Leah, and good afternoon, everyone. Thanks so much for joining us again. We've thoroughly enjoyed our webinar series the last several months. I hope you have gotten a lot out of it. If it's your first time, thanks for coming, and we'll share a little more about how you can access the previous ones. I'm very excited to talk to you today about understanding, optimizing, and analyzing thermal melts. It hit me the other day that I've wanted to do talk presentation like this for a very long time, and so I'm really happy to share this with you today. What I'd like to do is first review fluorescence with you and some basics of thermal melt curves, go into experimental design and optimization, and focus on how to get good data, everything from hardware to single point versus scanning thermal melts, uniform ramping versus stages, and then definitely close with analysis and data modeling, because that's often what gets the short end of the stick when it comes to analysis. People take the numbers that instruments spit out, and I think it's important that we take time to look at how those numbers are calculated. So before we get going, just a quick review of Jasco Corporation. Jasco has been making innovative scientific instruments since 1958, when it's got its start with a Nobel laureate spectroscopist. The corporation is located in Hachiochi, Japan. Our North American and South American office is in Easton, Maryland. And we have a broad palette of products that we offer in both chromatography and spectroscopy. You'll see here that we have everything from Raman and FTIR, including microscopy and imaging, SPM, HPLC, and SFC, circular dichroism, fluorescence, UV vis near IR, and vibrational circular dichroism. So quite an array of products. Today, I'll be mostly focusing on fluorescence and how that applies to the thermal melt application. But we'll tie in, because CD and UV vis are complementary, we'll tie in some examples from those. And a lot of what I'm talking about today is going to apply to all of these techniques. And since Jasco has them all under the same umbrella, you can use the very same software to run all of these systems and analyze the data. Now, as I begin and talk about fluorescence, just a quick reminder that we have done a lot of fundamental webinars. So I'm going to do a very quick review today to highlight important fluorescence benefits. But I have a full webinar back from in April that you can access on the web, both the recording and the PowerPoint. And the same is going to be true for UV and CD for more details there. So keep that in mind as we go through. You can certainly follow up after this presentation. But fluorescence is the radiant transition of the lowest level of the excited state of a molecule to any level, sublevel in the ground state. So we send a photon in, right? And we relax back down to the first level of the excited state, and we have a whole bunch of choices because of the vibrational levels in the molecule to which we can relax back down to. So we tend to get very broad and featureless spectra. Why would we want to use fluorescence? Well, many of you in the audience hopefully are just immediately saying sensitive, right? That's why we choose fluorescence. The second most important reason to do fluorescence is what? It's sensitive. That's really why we love fluorescence. So you can imagine the third most important reason to use fluorescence, gotcha, is selective, right? We have selectivity and sensitivity with fluorescence, which lets us tailor our experiments so that we can look at areas of greatest interest and minimize interferences, but also have awesome sensitivity. So because of that sensitivity, it's important that we understand what factors affect fluorescence, and it really is just about everything. So solution conditions, solvent, pH, ionic strength, temperature, concentration, right? So that's great. It's great that we have that level of sensitivity to local microenvironments around the fluorophore. However, requires careful experimental control because we want to make sure that the observed fluorescence changes are due to the experimental conditions that we intentionally modified and not just things that we didn't bother controlling. As we spoke about in the earlier webinar, there's just a whole suite of fluorescence applications across the gamut of biochemical, environmental, material science, food science. Today, we're going to focus on the biochemical arena, right? Because thermal melts, we're looking at a lot of protein stability, binding interactions, drug delivery, folding, aggregation. And that's why most of the talk, again, we're going to focus on tailoring everything towards fluorescence, realizing that the complementary techniques of CD and UV go hand in hand with this throughout. Now, it's so convenient for us if we want to monitor thermal stability, we need a probe to do that. And in proteins, we have the aromatic amino acids, tyrosine, tryptophan, and phenylalanine, which conveniently provide us this intrinsic fluorescence to study protein interactions and folding, right? So we're not doing anything else to perturb the system. However, there are times when we either don't have adequate fluorescence or it's not as well-defined fluorescence, and we can choose extrinsic probes that suit our needs. Maybe we want specific spectral characteristics, emission at longer wavelengths than the background fluorescence, or even just to be able to excite at longer wavelengths than the common biological interferences, or even autofluorescence that might be present. We might want a particular chemistry. We want to look at hydrophobic versus hydrophilic residues. So there's a whole suite of probes that are available. Just tossed a few names out here for you. Cipro, Orange, ANS are great for looking at hydrophobic residues. DNA, we can monitor via UV-Vis, right, absorbance, but we can also use a fluorescence probe, cyber green, and intercalate in the grooves of DNA. We can choose to react with a specific functionality and use a thiol reactive probe with whatever alphabet soup letters of probe molecules that are there. There's a lot of them. And equally important is we can choose probes that have a high quantum efficiency or strength of emission, so we further enhance our sensitivity. Now that we understand that, let's take a look at thermal stability. So thermal stability is just how a molecule or complex responds to raising and lowering the temperature. Greater thermal stability is going to be exhibited by species that maintain their initial state and don't transition to another state until higher temperatures are reached, like, say, a protein going from a native folded state to an unfolded state, or protein-protein ligand interaction dissociating. Greater thermal stability is evidenced by a structure's ability to return to its original state after repeatedly raising and lowering the temperature. So in other words, the more reversible or the more reversibility, the greater the stability. How are we going to evaluate this thermal stability? There's two common ways we're going to talk about today. One is melt curves, and they just simply monitor a signal like the intensity of a fluorescence, absorbance, or millidegrees, and at a single wavelength, or in the case of fluorescence, a wavelength pair, and how that changes with temperature. If we want more information, we could look at temperature wavelength scans, which collect a series of spectra as temperature is ramped to some final target temperature. Thermal stability applications are everywhere, right? If you're a biochemist, you're interested in protein structure, antibody structure, protein-protein interactions, protein nucleic interactions, ligand binding, in industry, pharmaceutical formulation, storage, dissolution, drug discovery, enzymatic robustness. Oops, sorry, a little quick there. Enzymatic robustness, right? We can go on, and you're listing some yourself right now. So that's great. Let's take a look then at evaluating the thermal stability in this example of proteins. So what we see here is actually a CD data in millidegrees versus temperature at a particular wavelength. We're looking at the native state of the protein here at this top platform. We have a transition, and at the end point here, we have the denatured state. So we can draw lines through the two flat portions of the curve, the initial and the final state. We can fit right along that transition, a nice straight line. And then if I bisect the difference between the initial and final state, you'll see I intersect that line, the transition line that is, and we call that the denaturation temperature, right? This at the top here, where we start to see the transition, is called the onset, and it's the temperature at which the protein begins to change from its native state. Now, the higher that onset temperature, the more stable the protein. So you already know from the get-go, right, kind of where you're starting. So let's look at this in a different way. We could get the TM, or the denaturation temperature, so software can calculate that. But in addition, our software also lets you calculate other thermodynamic parameters, such as delta H, delta S, and delta G. Taking a look at just the classic thermal melt curve, most of them are going to have this kind of sigmoidal shape. And we're going to be looking at fluorescence, absorbance, or millidegrees versus temperature. The inflection point identifies the melt temperature, or TM. And we have three regions, basically, right? You can kind of see that. We have an initial native state region, we have a region of transition, and we have a final state. Let's look at this in terms of an example. So riboflavin binding protein. It's a great protein, super robust, great for biochem labs. You can extract it from chicken eggs. And what we have with it is the holo complex. Holo RBP is the native folded state. In that folded state, riboflavin is bound in the pocket. Here's what free riboflavin would look like. And here's the apo RBP version, which is the unfolded non-native state. And you can see that the pocket is open, it's empty. How does that apply to the thermal melt curve? Well, let's look at the initial state. This area here, where we have a slight slope, is mostly holo RBP, which begins to transition into apo RBP, free riboflavin, and a mix of holo RBP with a 50-50 mix showing up here at the transition point. The end point of our melt, we have free riboflavin and apo-RBP. So let's look at some data. Repeatability. In this case, I have 3 thermal melt scans that were run from about 20 to 90 degrees, and the same sample, the exact same sample, not even just a different aliquot. The same sample was run day 1 twice, and then on another day, run again, and we have beautiful reproducibility, right? I mean, so clearly it folded up again, and this is a very robust, very reversible system. Not all systems are the same. So in this case, we're looking at CD data. And at the bottom here, we have the start of the thermal melt curve. And you can see, again, it's not, they're all different shapes. This one's not exactly S-shaped, but this is our sigmoidal shaped curve. Going from 20 to 65, we could easily calculate a TM. However, when we do the reverse runs, you see these flat lines at the top, all right? It does not return to that initial state. And this is true of many systems. So it's more often than not, things are not reversible. And that's what the goal is, right? To try to make changes so that we get a greater robustness and reversibility. Now, scanning wavelength thermal melts are going to give us a wealth of information, right? Because now, if you look at this, we've got, in this case, fluorescence intensity, wavelength scan, and then the temperature at which each wavelength scan was run. So we get this 3D matrix. This is for RBP. And basically, we get to capture a bigger picture of what's going on with the sample. We can monitor scatter contributions and aggregation, observe the presence of unexpected species. And to boot, we still can extract thermal melt curves at multiple wavelengths of interest. So it's a real bonus to be able to run scanning thermal melts. Now, with that said, this applies to not just fluorescence, but UV vis and CD thermal melts for all Jasco systems. Another way to look at the thermal scans is just to stack them like this. So I have fluorescence versus wavelength, and each scan is at a different temperature here from 25 to 90. Looking at apo-RBP, we're going to excite at 280, and we're looking at the wavelength scan from 270 to 600 with this data interval. Every 2 degrees, we're collecting a scan at that ramp rate of temperature change. So what do we see? Well, right away, hopefully those of you who've done protein fluorescence noticed this and said, hey, that's tryptophan. That's the at the excitation and emission wavelength of 280, 345. But we have some other things present, right? And so maybe those of you who are a little more savvy with fluorescence or spectroscopy realize that here we have some important bands that I always like to include in the scans. These are Rayleigh and Raman scatter. And again, I go into a lot more detail about how to manage these in the earlier fluorescence webinar application. But here, looking at this, you can see they're not interfering at all with the band of interest. And that's why I like to be able to see that and monitor its behavior. There's also this slight bump down here, which we'll talk about shortly. So now here is the holo RBP thermal scans under the same conditions. You can see there's a lot more going on, and we might understand a little bit more about that bump. So this is the tryptophan. This is the extrinsic riboflavin fluorescence. So if we excite at 280, gives an emission at 530 nanometers. So this tryptophan peak is actually decreasing, and we're seeing this peak here for the riboflavin increase as we go to higher temperatures. Still, we see the scatter. In fact, now what's nice, I can see that for one of the scans, there's definitely a different scatter parameter. So it's good to be able to monitor that. And here's the Raman not really contributing as well. So lots of information, but what do you do with that? How do you calculate a thermal melt, a TM from that? Well, what I've shown here is a 3D plot, and you can see we can pull slices out of these. So if I pull out a 345 nanometer wavelength emission slice, I'm looking at the tryptophan fluorescence thermal melt, but I can do the same with the riboflavin one at 530. Interestingly enough, it was a wonderful surprise to have a corroboration of the TMs, both being 62. But wonderful that we have all of this information, right? So how do we get the most from our scanning wavelength, thermal melt curves, whatever technique we're using? My recommendation is to start with these as a survey to determine the best wavelengths to monitor in the single point melt curves, right? I mean, also you get to see what else is going on, right? You can make sure you're understanding nothing strange is going on with the system. But once you determine the best wavelengths, you can, well, these are run faster, right? Because you're using less temperature resolution. So you can kind of go through and do a quick run. But once you know what wavelengths, you can extract the melt curves and then identify the temperature range of greatest change in fluorescence, CD, or UV signal. And that's powerful, right? Because I can quickly get this and quickly determine where that transition change is, and then build an efficient single point thermal melt that has, we'll talk about this more later, a multi-stage profile in which we really tailor the melt curve to optimize data collection in the range of greatest change. Here's another advantage of reversible processes looking at some CD data. So on the left here, you see we have 3 curves. We just extracted 3 of them out. So started at 20, went to 100, and then went back down to 20. Notice that the 20 initial and 20 final curves lay beautifully over top. Lovely, very reversible. And it appears to be that way in both plots. However, and I should say on the left plot, you know, you might argue, well, we could just do a single point scan. There's not really any extra information gained by the scanning plot, but it's nice to have the picture and confirm that. However, with the right plot, I don't know if you can see this, but we now have a shift. And if we were just monitoring standard wavelengths for the single point melts, we would not realize that there was this shift to shorter wavelengths at 100 degrees and not be aware of that change in secondary structure. So the full spectral scan data is really powerful. So given that, how do we set up our experiment to get good data? Because that's the key, right? Everybody can get data. We want to get good data. So let's start with just simple, the cuvette, right? And hardware. Well, what technique are you going to use? That's pretty straightforward. If you do that technique, there's different ones that are appropriate for UV, fluorescence, and CD. More important probably is even the sample volume that you want. So I have a whole slew of cuvettes and holders listed over here, shown over here. You can see we have everything from your standard microvolume cuvette to multi-channel 10 microliter 8 well cuvette, right? But then things like stirring, is that something you need to do? You're not going to be stirring in these, so hopefully convection, you know, covers it for you. What kind of material? Oh my gosh, hopefully you all just said, of course, quartz. Black mass quartz is better, right? And what's the Z height, right? If you're using microvolumes, if you're a biochemist, you want to use as little as possible because you get more experiments that way and your sample is precious. So optimize all those. Now, what I'd like to focus on are these 3 here. So for thermal melts, if you want to stir, you might want these cuvettes. They're small form factor cuvettes. They're not as common, but if you do need to stir, they're great because you can now use a little stir flea in a 3x3 or 5x5 small form factor cuvette with a jacket that'll conduct the heat, and you can run your experiment. The other one that's really useful are the low headspace cuvettes, and they're different in that they have this huge cap which actually dips all the way down to the top of the window where your sample is. And that's important because upon heating then, you don't have evaporation up towards the top of the cell or change concentration, and we make sure that that window stays completely filled with sample. So these are the best for thermal applications. The other big question is hardware, single cell versus multi-cell. It's going to come down to a number of both scientific and cost kind of factors. Single cell Peltier, well, there's no moving parts, right? So it's really robust. Minimal alignment concerns, you just have to make sure you have the right Z height cuvette. Temperature consistency, you're not wondering about, cell to cell variability. And it's a lower cost. So a lot of folks like this. However, I can tell you from experience, there are a lot of advantages to the multi-cell Peltier. Number one being you get to do multiple samples. It's not like RT-PCR. You're not doing like library screens, right? But you have four cell holder in which you can run replicates. You can do different conditions. You can save time by setting it all up, walk it away, and doing other things. And what I like too is that you can sacrifice a cell position to monitor solution temperature in a cuvette with a temperature probe. So you don't have to worry that the probe is sticking down into the optical beam or contaminating your sample. It's a really great way to go, and that's what I recommend if you can. So how about setting up the parameters for the experiment? Again, I'm going to focus on fluorescence here, but most everything here will apply to the UV and CD spectroscopies, except for this part, right? So wavelengths, we have excitation emission wavelength pairs in fluorescence. In the single point, multi-point program, you can have up to 4, and that allows you to monitor several points of interest. You can monitor scatter and aggregation. And for UV and CD, you can even do up to 8 wavelengths. With, again, slightly different parameters, we're looking at just single wavelength. Spectral bandwidth is critical, right? That's needed to adjust sensitivity and discrimination if you're using multiple species. Response time, bonus with single point data, you can just increase the response time and have really nice low noise data. Sensitivity, the detector high voltage, right? Just as normal. This is all reviewed in the earlier presentation, but you're going to set it for the maximized sensitivity to the change in fluorescence. So what's important with thermal melts, right? Sometimes the fluorescence signal could start low and go high. Sometimes it'll start high and go low. If you're starting low, you got to figure out what it's going to be when it gets to that high temperature, high fluorescence value. And so you might run and do some practice runs initially to be able to optimize that setting. Now to the heart and soul of this, right? Setting the temperature profile. Well, start temperature, that's a good beginning. Important to keep in mind here though, if you are going to go down below about 15 degrees Celsius, it's critical to use dry air or nitrogen in the sample compartment because it prevents condensation on the cuvettes and optics. Setting the temperature profile. Well, this is it. These are the parameters that we care about. We want to be able to set the data interval. That's important. It's going to control the data density. So how often do I collect temperature data? What is the target temperature that I want to finish the run at? What is the ramp rate? Do I want to go fast and do a quick run? Do I want to go slow? And do I want to wait time at each temperature so that I'm confident it's equilibrated to that temperature and that the temperature of the block is the temperature of inside the cuvette. reverse run. So we have the flexibility. You can click that box, and it actually allows you to run this same profile that we set up here. It will finish at 90, and then if you set a hold time, it'll wait at that hold time, and then you can go and it'll run the exact profile backwards. So you can immediately test reversibility that way as well. Now, this is a conversation worth having, monitoring versus controlling temperature. So set how the temperature is controlled. There's a control sensor, and that control sensor drives the Peltier to the target temperature in the profile, okay? Now, that control sensor can be based on the temperature of the holder or based on the temperature of inside the cuvette, right? The temperature of the solution. So it's important to decide which one of those. Obviously, the most accurate is going to be inside the cell. However, the other aspect here is monitor sensor, which is what is plotted, right? So the actual data that is included in your melt curve then is from this control. And again, you can choose holder or the Peltier block or the in-cell sensor. No doubt about it, right? If you've done any kind of higher temperature measurements, you know that that Peltier block will get to 80 degrees way before the temperature inside the solution inside that cuvette. So as much as possible, you should use the in-cell sensor to have the most accurate data. So let's look at some proof data on this. Here's a UV thermal melt example using a model similar to our current V730. A 6-cell position Peltier allowed us to do these replicates. Very simple 20 mg per mil solution of poly DADT, and the 8-channel micro cuvette that has the 10 microliter wells, where 7 were used for samples and 1 was sacrificed to monitor temperature. Okay, so these are the conditions and these are the curves that were obtained in 2 different setups, right? One, we're monitoring the holder sensor, and the other, we're monitoring the internal cell sensor. Well, they look pretty darn similar, right? Let's look at the actual TM calculations. Okay, well, a quick glance down here, we can see we're right around 66.1 for the holder sensor. For the in-cell sensor, however, we're about 2.5 degrees lower. So both data sets, I mean, show up really reproducible if you look at the numbers, right? So great reproducibility, very low standard deviation in CV, but it's clear that the in-cell temperature sensor is going to give you the most accurate TMs. Now, we kind of skipped over this earlier. You may have been wondering what these extra rows were for. Well, this is the exciting part. You can set up stages. And these stages allow the user to optimize the frequency of data collection and the temperature ramp rate over specific desired ranges. So let's take a closer look. Here I have a thermal melt curve, and to collect this curve, 5 stages were used. So the stage that I've highlighted in yellow, 1 and 5, are kind of on the flat portions of the curve. So I don't need as much data to clearly define that. I don't have to go at 0.1 degrees Celsius steps. So here I have a faster ramp rate and a greater temperature collection interval. However, right, there's the area of interest, right, where we have the greatest change, where I want to really have a lot of data, great data density, I like to say, so that we can accurately define and calculate the TM. So here we've dropped down to 0.1 degrees, steps and a slower ramp rate. And you could go slower, but honestly, once you're going at 0.1 degree steps, you don't need to. Now, these other two regions are kind of up to the user. I personally find it helpful to maybe put these somewhere in between because I'll show you in data analysis, it helps to maybe more clearly define this slope, and having a little more data there is useful. So we have efficiency of collection time because now we're not collecting the whole melt at 0.1 intervals. So we can go fast where we need to go fast, and we can go slow where we need to go slow. We get accurate calculation of our TM and preservation of sample integrity because now we've decreased the collection time and minimized the heat exposure of our sample. All right, coming to the home stretch for parameters, start and stop conditions. I really like the choices that we get in the Jasco software. We can control, you get to choose how to get to temperature. So you can say, hey, keep it within, in this case, 0.1 degree for so much time. You can say, no, I'd rather cross the target temperature X times to be sure that I'm hovering at the right temperature and I'm not just passing it by. And you can ensure that it has equilibrated by having a monitor temperature stable condition so that it's within a certain range of the target temperature for a determined amount of time. You can also choose how to end the experiment. Stay at current temperature, return to start temperature, or move to a specified desired temperature. All right, it's the little things that count. So this might seem trivial, but I love this. We have software control of the stirring. And, you know, there's those of you sitting in the audience, I know you're saying, yes, you know, you're trying to turn the knob and get it to go to the speed you want to, or you have it set and then somebody else in the lab comes and changes it. All right, here, you just set it in your method and you're good to go. You get software control for consistency and you get faster and uniform thermal mixing. Again, it's small, but it's those kind of details that really help with doing good experimentation and enjoying it. All right, so we've talked about thermal melts. We've talked about how to get good data. We have to spend a little bit of time talking about data analysis and modeling. And I bring this up because, again, too often it's just whatever the program provides, right? Oh, it knows what to do. So I'm going to make some suggestions for you to devote more time to data analysis. Try to learn about the programs and try different ones. Understand the calculations and models employed. I know it takes time. You have to look at the manuals and talk to the provider and all that, but it's worth it. Be aware of limitations and determine when it's best to use the different methods. Try to vary analysis parameters and see how sensitive the results are to the changes, right? Some parameters may not make a big difference at all. You don't have to worry about them. And others, you're like, wow, I have to watch that. And I want to be consistent so that when I reanalyze data, I'm using the same approach. And then finally, analyze replicate data, right? Like analyze the very same data in different ways and then analyze replicate data. And let's do some of that now. But first, I think we should talk about what methods are used to calculate TMs. Recall that they are the inflection point on the sigmoidal shaped curve. So there are two main ways to calculate them, from single point and scanning thermal melt data. The most popular one by far is second derivative, right? Second derivative equals 0 at the inflection point due to the change in concavity and the change in slope, okay? Least squares is another method though, and this it was nicely illustrated when I was defining thermal melts for you. We basically fit a straight line to the area of greatest change, and then we also fit straight lines along the starting stage of the melt and the final stage of the melt. And we're able to use a line then that bisects between those two start and final. It bisects that greatest change and calculate the melt temperature. So what about second derivatives? Let's just take a look at a screenshot of this. This is a holo RBP, and so this next set of data is just the exact same data file that we're going to look at, okay? In this case, I have second derivative selected down here. That's the sample I'm looking at. Here is the melting temperature that's provided. If I would have checked some other boxes, we'd also see delta H, delta S values provided. Didn't do that for this talk. Notice that we have a rectangle here, and that rectangle is user selected, and it highlights the area used for the fit. Okay, you see that there is a red line overlaid on the data, and that red line looks like it fits actually quite well, so that's good. So this range that I've selected is probably a good range to calculate the thermal melt. So what if I move this, extend or decrease this rectangle area, right, the area of analysis, same data using a broader range? Well, you can see the pictures here, and I zoomed in, get pretty good overlay here still on this second one. You can see the TM values are very close. However, when I just go and I just really broaden out the range, you begin to see where I lose the fit, right? Now, it's not a huge change, but I mean, thermal melts, you know, if you want to keep them as tight as possible and look at smaller changes, I have almost a degree change there. All right, so that selection of the area of analysis will be important. What about the least squares method then? Well, again, it's the holo RBP, exact same data set. So remember, like we said, we have these lines that are drawn that kind of try to carefully trace the start and the stop stages. Then a line is drawn which bisects those two, and where that intersects is the TM. So for this one, I get a 63.05. And what I'm doing is I have different rectangles, right? So now I have two rectangles. This rectangle defines the range I use to draw a line on the initial phase, and this rectangle defines this line for the upper boundary. So you can see if I go too shallow and I use just a couple data points in this second example here, that greatly impacts my thermal melt value, 62.46. Here, you know, I made some small changes. I made this larger, made this smaller, and 63.37. So what you'll see for the exact same data set, depending on how I analyze it, I can get over a degree difference in the analysis for the thermal melt, right? So consistency and doing this so that you're confident with how you're analyzing the data and that you're doing it consistently is going to be important. Well, this is really quite pretty data, right? And you might also be asking, well, how do I even know, like, why would I use least squares versus second derivative? Well, let's look at this next set. So we have bovine gamma globulin samples that were run by a customer. And in this case, you'll see, so not all thermal melt data is pretty. Some interesting things can happen at higher temperatures for fluorescence. So in looking at this right away, like to myself, I say, wow, I probably don't want to fit a line to this or to this, right? So the least squares method is probably not the best way to go for that. So best to use the derivative method because, I mean, defining along that curve there is great. And actually, I can get very, oh, sorry, that's a typo. That's supposed to be 69.45, 69.58 and 69.45. Very, very reproducible data for two different samples here, not the same data set, two different data sets. So in summary, I'd like to just give you a few take-home messages. Thermal melt studies can provide valuable stability data to better understand protein folding, binding events, nucleic acids, a whole wealth of applications and assist in identification of molecular candidates with desired properties, right? You make a change. Does that change give me the property I want? Which one of these is the best? You can use single point and scanning wavelength thermal melt data together in combination to construct a more complete view of changing chemistry and structure. And combine multiple techniques like fluorescence, UV-Vis, CD to get additional supporting information. It's always nice when more than one technique supports or fills in information on a complex system. And then these last ones are real important, right? Set collection parameters carefully. In particular, don't make assumptions, right? Don't make assumption that the temperature being recorded is the temperature inside the cell. Make sure you know that by how you set up the experiment. And also take advantage of multiple temperature stages to ensure that you get efficient data collection, highest quality data in the region of greatest change and transition. So where we need that detail the most, right? And finally, put more time into conducting and understanding data analysis. Change analysis parameters. Don't be afraid to. Note how it impacts the calculated value and make decisions from there. Got to give a few acknowledgments. Really like to thank the folks, Aaron Drake and Dr. Levi Milkey at University of Indianapolis Chemistry Department. They provided actually a lot more data than I had time to show, BGG thermal melt data using glow melt. And at Capital University, the chemistry department, Joshua Tomsick and Dr. Tracy Murray collaborated with me in work we did with RBP thermal melt data. So thanks to them for all their contributions. And have to mention the resources again. I'll let you know we've put a lot of work into these webinars, so please go to our website, check them out. I think you'll find a lot of good information there. There's also ebooks, tips and tricks, posters that are available for a variety of techniques. Our knowledge base is a wonderful place to start if you want to know more about a particular application area in the peer-reviewed literature. And we've had a lot of fun, but we're taking a break from webinars in July. We will start up again in August with 2 exciting speakers. And so I'd like to just highlight for you that we'll start again on August 4th at 2 p.m. Eastern Daylight Time with Dr. Luis Rodriguez-Sayona. He's from Ohio State, Department of Food Science and Technology, and has done some really groundbreaking work looking at metabolic fingerprinting for diagnosis of fibromyalgia and other rheumatology disorders using Raman microscopy analysis of blood spots. In addition, have a little bit different take the following week. Dr. Andrew Jacques from Water Quality Investigations, a former professor that started his own company. So interesting, you can check that out on his website. We'll be looking at excitation emission matrices as fluorescence fingerprints of biofilms, a unique approach to assessing, remediating, and troubleshooting water quality and biological treatment processes. So there you go. I really want to thank you all for joining us today. I hope you got a lot out of our webinars, and especially today, and we're happy to take any questions. I have with me Dr. Leah Pandisha, who is our CD, fluorescence, and UV application scientist, and she will work with me in addressing your questions. Thank you. It'll just be a second as we pull up the questions. The first question I see is, can we also measure the temperature melt curves or phosphorescence from crystals? That is really interesting. So when you say from crystals, so now you're talking about solid phase. So you have to make sure you had a holder that would address that. I mean, I suppose you could put crystals in, you know, just a standard kind of small form factor, maybe cuvette, and monitor that. Maybe we should talk more about that offline, but you certainly should be able to do that kind of melt. And I'd be curious to know more about what you'd like to accomplish with that. Let's see. go. Can you obtain thermodynamic parameters from an irreversible melt? Well, I think Leah will quickly address that one. No. But Leah, do you have more to add to that? That's definitely more up your alley.
No, not really. I think one of, there's two other questions that I think I've also sent to you. One of them is about temperature ranges for our instruments too. I'm not sure if you got that one yet.
Oh, sorry, I'm having a little trouble getting the expanded view. So,
No worries.
yeah, so temperature ranges, again, it's really important, I think, that you have a broad temperature range. So for CD, I think the range is like, well, you know that one, it's like minus 30 to 100, but like in terms of like usable range, I think most instruments are 0 to 100. And of course, to get down to the low temperatures, it's usually important to chill the coolant. I mean, it's a Peltier, but even Peltiers require you to be able to pull the heat off for efficient temperature control. I see one here. It says, do all cuvettes have internal temperature readings? That's a really good question. So you can do that. You have that flexibility. So like for that 6-cell Peltier where I showed data, and for the fluorometer, that's the 4-position multi-cell, you can have a probe for each cell position. I think we have data demonstrating the cell-to-cell variability is minimal. And so usually just using one cell is adequate, but if it's really important to you, you can do that, yes. Let's see. Leah, I might need your help here. I'm still trying to get that question released.
Sure. Another question we have is how to select the gradient and interval for the melt.
Oh, that's a really good question. Yeah. So let's see, maybe if let me just go back a second to that slide. So, how do you know where to do this? So my recommendation again is going to be do an initial thermal melt. Just let it go. Look at the shape of the curve and figure out, like, is it a beautiful, much more S-shaped curve? How sloped is this, right? I think you definitely have an advantage to doing at least 3 stages, right? And usually those stages would be, this yellow region covering this area of greatest transition, maybe these 2, and then a 3rd stage here, right? But, I can say that, but the best way to do it is to try some different stages and see how it impacts your data. Sure, it takes a little more time, but if you're going to be doing a lot of these, it's well worth optimizing your data. And it also ties into how long you need the run to go too, right? If you need a faster run, you're going to carefully select your ramp rate and data density to account for that as well. Okay, let's see, do we have other ones? Is there an example protein that can be used to practice on? Good question. And yes, well, I mean, there's several. So the folks at University of Indianapolis used BGG, bovine gamma globulin, just like to play with and get comfortable with doing thermal melts. So you can just buy that stuff. If you're hooked up, or if you have access to a riboflavin binding protein, I love it because it just is so easy. And it's great for academic teaching labs too. So if we have any folks like that here, I can hook you up with some professors, well, the one I collaborated with at Capital University, Dr. Tracy Murray, who uses that in her biochem lab. And they isolate that, purify it, and then do thermal melts with it. Let's see. Do fluorescence spectroscopy have same intensity, is same across instruments, is same throughout instrument lifetime? Oh, okay, so basic fluorescence question. So that's, you know, fluorescence is sensitive, right? But, and you do, it's a ratioed measurement, but it's not an absolute measurement. So it's not going to be the same across instruments. It's not going to be the same across the lifetime of the instrument. And so there are ways you can use quantum efficiency counters. You can do ratios. So one, I would love to have shown you more data. One easy way to account for fluctuations in signal, which are going to happen over time, is to do ratiometric measurements. So measure, instead of just looking at, say, the 345 for tryptophan, look at the ratio of 345 to 530 or to some other wavelength you've selected. That would be my recommendation for that one. So that's the same question. Sorry, I'm scanning through here. I think there's another one I haven't gotten to. Oh, wow. Okay. Yeah. So life is not always so simple as a two-state process. This question is, how would you approach analysis of the melt for thermo parameters if the protein does not follow a two-state unfolding process, but rather a 3 or more state process? All right. So as you get, and that's the beauty of stages, right? I think, you know, there are definitely examples of thermal melts being done for those. And that's where you do a run, maybe at a single ramp rate, see where these changes are, and then optimize each of those steps with different stages for your data collection. That would be my recommendation. And then definitely, if it's that complicated, make sure you're doing scanning thermal melts as well to really get a bigger picture of everything that's going on. Let's see, Leah, do you see? Oh, here's another one. Oh, good question. Do the single quartz cuvette, for instance, the 1 millimeter, have temperature probes as well as just Peltier cuvettes? I think what you're asking is, yeah, you can do temperature probes in all different kinds of cuvettes, basically. The probe for Jasco is designed, you know, you just have to have it fit through a lid. So yes, you can use for like the 10 8 well 10 microliter multi-channel cuvette. You can have probes in those as well. And yeah, so that's the long answer. Short answer is yes.
Sherry, I just wanted to clarify something about that kind of went off of the two-state unfolding processes and irreversible and reversible models.
Oh,
because I don't think we emphasized that. But you can obviously get thermodynamic parameters for irreversible processes. It's just not with our current software. So it would have to be something where you exported the thermal melts that you acquired.
Oh, sorry. Yeah, that's a good point. I should have said that. I mean, that's what a lot of people do too, right? I mean, so you get the advantage. We have great capabilities in our software, but people, you know, we have a lot of folks in the biothermodynamics community that, you know, have all their own programs, and yeah, you can certainly export the data and analyze to your heart's content that way. Are there more, Leah, or is that all I'm seeing?
I believe you have gone through all of them, and we are out of time anyway, so we conveniently ended perfectly. I just wanted to thank everyone for attending our thermal melt webinar, and if you would like to reference this webinar or see the PowerPoint, you can visit our website, jascoinc.com, and access, I believe, it's the applications link, but we also will be sending out emails to supply you with the information from this webinar, and you can again reference any of our previous webinars at our website as well. I just want to thank everyone again for coming, and have an excellent week. And thank you again, Sherry.
You're welcome. Thanks, everyone. Feel free to contact us. We'd love to talk to you. Bye.